Hello, my name is Zachary Zhu, and today I will be talking about slope fields. So what exactly is a slope field? A slope field is a graphical representation of differential equations and the solutions to differential equations. Differential equations are equations in the form of dy over dx equals f of x comma y. F of x comma y is just any arbitrary function. For example, it could be x times y, x divided by 2y, or x plus 2y. dy over dx should look familiar because that just represents the slope. So let's go over a sample problem. Say we have the differential equation dy over dx equals x minus y. In order to graph the slope field, we first create a table of values. At the point -1, comma -1, the slope is equal to -1 minus -1, which is equal to 0. At the point 0, comma -1, the slope is equal to 0 minus -1, which is equal to 1. At the point 1, comma -1, the slope is equal to 1 minus -1, which is equal to 2. And we can continue with that process to find the slope values at each of these points. Now that we have a table of values, we can graph our slope field. In order to graph the slope field, all we have to do is use the slope that we found in our table of values and then draw a little dash that represents the slope at that point. At the point -1, comma -1, the slope is equal to 0, so we just draw a horizontal line. At the point 0, comma -1, the slope is equal to 1, so we just draw a line, small line with a slope of 1. At the point 1, comma -1, the slope is equal to 2, so we draw a steeper line. At the point -1, comma 0, the slope is equal to -1, so we draw a small line with a slope of -1. At the point 0, comma 0, the slope is equal to 0, so we just draw a horizontal line. At the point 1, comma 0, the slope is equal to 1, so we draw a small line with a slope of 1. At the point -1, comma 1, the slope is equal to -2, so it's really steep downwards. At the point 0, comma -1, the slope is equal to -1, so it's not as steep downwards. And at 1, comma 1, the slope is once again 0, so it's just a horizontal line. As we increase the size of the slope field, we can get a better representation of the differential equation. Now let's practice graphing specific solutions to differential equations. Say we had the differential equation dy over dx equals 2x minus xy. We can factor that to x times 2 minus y. We know that dy over dx equals 0 when x equals 0 or y equals 2. We can create a table of values to find various values of slopes for various combinations of x and y. In general, we observe that as the x value gets further away from 0, the absolute value of the slope increases. As the value of y gets further away from 2, the absolute value of the slope also increases. Eventually, we can create a slope field like this one for dy over dx equals 2x minus xy. Now we want to find the specific solution that goes through -1, comma -1. In order to find the solution, first we graph the point -1, comma -1, which is somewhere around here, and we follow the slopes on both sides of the point. On the left side, the slopes seem to be increasing, then eventually level off as the point approaches y equals 2. So the solution would look something like this. And on the right side, the slope seems to be getting more steep and more steep until it gets sufficiently close to the y-axis, and then levels off, and then the slope becomes positive and begins to get more and more steep, and eventually levels off as once again it approaches y equals 2. In this case, both of the values will be getting infinitely close to the value y equals 2, but we'll never get there, so y equals 2 is an asymptote for this equation. Now, let's practice matching these slope field graphs to their corresponding differential equation. For the first slope field graph, we clearly see that there is some sort of domain restraint. It only exists for values x is greater than or equal to 0 or when x is greater than 0. This behavior matches equation C and equation D. To see which one it is, we can check the value of the slope when x equals 1.
If it is equation C, which is dy over dx equals ln of x, then when x equals 1, the slope should be equal to 0. However, in this graph, this is not the case. When x equals 1, the slope is equal to around 1 as well, which matches equation D, which is dy over dx equals the square root of x. For the second graph, we once again see that there's some sort of domain restraint. It only exists for values of x when x is greater than or equal to 0 or when x is greater than 0. Through process of elimination, we see that this must be graph's equation C, which is dy over dx equals ln of x. To check this, we can see what the slope is when x is equal to 1. When x is equal to 1 for this graph, the slope is also equal to 0, which matches the behavior for equation C, dy over dx equals ln of x. For the third graph, we clearly see that the slope is equal to 0 when y is equal to 2. So this graph must match either equation A or equation B. For equation A, dy over dx equals xy minus 2x, the slope is equal to 0 when y is equal to 2. For equation B, dy over dx equals 2x over y, this is not the case. When y is equal to 2 and x is equal to any value other than 0, the slope is not equal to 0. So therefore, graph 3 must match equation A. Through process of elimination, we know that graph 4 must be equal to the equation B. To check this, let's see what the value of the slope is when along the y-axis. Along the y-axis, when x is equal to 0, we clearly see that the slope again is equal to 0. This type of behavior matches equation B, dy over dx equals 2x over y. By observing this kind of behavior, we can determine the various differential equations for various slope fields.
Now I'm going to show you how to graph slope fields in your graphing calculator. For the TI Nspire, I believe that there is already a built-in program, so I will be showing using the TI-84, which also works for the TI-83. So in order to do this, copy the program, which I will give you a link to in the description of this video. Afterwards, make sure your window is scaled properly. -10, 10, 1, -10, 10, 1 should be good for our equation, which is going to be y plus x. And afterwards, all you have to do is click program and then execute the slope field program. And then you click enter one more time and you can see a very clear slope field. So it's very convenient to use a graphing calculator because that way you don't have to plot each individual point and each individual slope. So that's basically how you use a graphing calculator to graph slope fields. Now let's go over some common sources of errors for slope field problems. Make sure you check for value restrictions for differential equations of ln of x and the square root of x. Also, make sure you graph the slope rather than an individual point. Say you wanted to graph the solution of a differential equation that passes through 1, 1. Make sure you actually graph the line that represents the solution rather than just an individual point. Also, make sure you do not graph slopes when the denominator equals 0 since the behavior is uncertain. For example, if you had the differential equation dy over dx equals x over y on 2, 0, we're not exactly sure what the slope is equal to, so we avoid graphing that equation on that point.